trying to get physics all a little bit more. Right, I'm probably gonna dig with all of a sudden. Like from 8.
How's physics going? Yeah.
Not great. Miscellaneous. Basic supposed to like you started pulling pages out of the textbook and it's like, and this is how you would divide, but I'm not gonna make you do that. And then he would flip it. He's like, and this is another equation. But I'm not gonna make you do that. What? And then he showed us like good 6 examples. And I was like, how do you do this?
All right. Any announcements before we get started? Or questions or anything? So of course, don't forget midterm is next week. So we'll do, again, like I said, midterm review on Tuesday.
Oh, what day is it? Thursday?
Yeah, so the midterm will be on Thursday, review Tuesday.
I have like extra time.
If you have an accommodation, then you'll probably have to go to the testing center to do that. So you can email me, otherwise we'll have to try to piece through your accommodation letters. But other questions?
I have a question.
Yeah.
Is that going to include chapter 5 or is it chapter 1 through 4?
It'll include chapter 5, yeah. Other questions? All right, so let's finish up the last little bit of chapter 5. And so the last little bit here is now just emphasizing our periodic trend of atomic radii, which I feel like we've kind of talked about before, but we're just going to kind of re-solidify again with our electron configuration and all the orbitals, how we've been going over them in more detail. And so, of course, these are the elements plotted by their atomic number. And, right, we can start with, okay, the alkali metals, obviously, right, increasing atomic radius as we go down the periodic table. We've, said that, and again, right, we can think back to our increasing onion shells as we add more energy levels. And then notice, of course, as we go across the periodic table, the radius tends to decrease. And again, that goes back to the concept of the effective nuclear charge. And so you can, again, just think about that in detail. So let's just compare. So looking at the 2p, if we just take, let's just look at lithium, why not? So lithium, right, only has 1 electron in the 2s here. And then if we compare it to, let's just compare it to oxygen, right? So now oxygen, 6 valence electrons, 2 in the 2s, and again, right, as we go across the same second energy level, we add more electrons. We essentially have, again, more negative charge at the same radius distance, and again, from that kind of rough formula, right, of charge 1 times charge 2 over r squared with whatever coefficient, right? Again, roughly, if we're having more charge, then that's going to have a greater attractive force, which decreases our radius. So we see that general trend, and then of course, right, transition metals, things are going to be funky there. We're not going to talk about it right now, but again, we kind of gotten a little hint as to why they're funky with the d orbitals, and so again, they can become not degenerate basically, but that's why it's funky. But again, we just go with our basic trends. So increasing radius as we go down, and then of course decreasing as we go across. All right, so let's do some review. So let's just start with this problem. So what is the uncertainty in the velocity of an electron whose position is known to within 2 × 10⁸ meters? And so if the electron is moving at a speed of 5 × 10⁵ meters per second, what fraction of the speed does this uncertainty represent? So take a few minutes to look at that. And I'll give you a little piece of information just in case. So mass of an electron, if you didn't find that in your notes, it's 9.109 times 10 to the negative 31 kilograms, so that should help. So see if you can finish plugging that in. So what formula do you need? And then see if you can do that second part. So what fraction does that represent?
And she was sending an email asking about how to access the Zoom via Blackboard because she can't figure out how to find it. So
I
she asked
messaged
me-
her.
You did? Okay, cool. Thank you.
But there's a link in Blackboard that she should have seen. So what formula do we use for this one? What is this related to?
The wavelength?
Hmm. So, yeah, it's not asking about the de Broglie wavelength, but what was that other, what was the thing about uncertainty?
I don't believe we've gone over it.
I think we left off before.
Oh, we definitely went over it. We just didn't do any problems. You guys got a lot of studying to do. That's all I gotta say. Okay, so let's find it in our notes. So, right, we had done this Heisenberg uncertainty principle. So I'd given you the formula. So yes, we did go over it in class. We just didn't do a sample problem. So we're doing it now, but right, there's not too much to go over. So we have our formula. So we have, right, this principle. So, okay, we said that we can know something to within this degree of certainty. So, right, this is a formula that we should start out with. So then that's our first step. So our uncertainty in our position times, again, uncertainty in momentum, which I like to write it as, which then we want to recognize, okay, momentum is going to be our mass times velocity. Now we can start plugging things in. And so it says, okay, first we need to figure out, right, the uncertainty. So it says, so what is our uncertainty of our velocity? So our position is known, right, to within this amount. So there's our position. But now we're trying to figure out, well, what is a certainty in my velocity? So we need to calculate that. So we can plug that in.
Can you post the live notes, please?
I thought they were posted. I can look again.
It says content unavailable to review when I try to open it.
Oh, that must be a Blackboard error. I don't know. Yeah, I would just refresh and try again because they should be going. Do other people access them okay? No? All right, well, I will have to figure that out not during lecture time. So again, I apologize. All right, so so try to do that. So where are we at? So now plugging it in. Yeah, if the live notes don't work, I'll just have to export a PDF at the end, but like I said, I can't fix anything on my end at this point. So now just math, and then what was H again? So Planck's constant, excellent, 6.626 times 10 to the negative 34.
Can you come over where the 4 pi comes in from again?
It's just from the formula. We didn't really go over exactly how he derived the 4 pi. We're just accepting it, yeah. The derivation would be. All right, so now algebra. So I'm just plugging in this first. And then don't forget to put parentheses around your 4 pi, also order of operations. And then, so divided by. All right, so now we should have something like this. So basically, right, the uncertainty in our velocity is 2,894 meters per second, right? So that's our unknown factor, right? Our margin of error, essentially. And then, so the problem asks, okay then, so given this uncertainty in its velocity that we just found, if the electron then is moving at a speed of 5 times 10 to the 5th meters per second, what fraction of the speed does this uncertainty represent? So then that's just asking you to take this answer and then, of course, dividing it by the measured speed to, again, figure out kind of our margin of error here. So times 100, and, you know, actually not too bad, like 0.6% error roughly, so. Questions on that one? All right, so let's try the next one. And so now this is asking, okay, we have a following set of quantum numbers, right? So we have 1, 2, 3, 4, 5 different sets here. And then it's saying, okay, out of these 5 sets, so which of them are allowed? And if something is wrong with it, that it's not allowed, then how could you correct it? Okay, the notes should be fixed. I just redid it. So let's go through them. So what about the first one? Is this allowed, unallowed?
That one should be allowed.
So allowed, and then can you maybe give an example of maybe like what element it could be?
N is 2, that's in the second. L is 1.
So L is 1, so what orbital is that?
That's the p orbital.
Excellent, so right, p orbital. And then, so what would be a potential element?
3 electrons in the p orbital or 6 electrons in the p orbital.
Well, we don't know from this information, so all we know is that it's a p orbital, right, on the second energy level. So it really could be, anything. So anything on that second row, so looking at our periodic table, right, could be boron, carbon, nitrogen, oxygen, right? We're just saying, okay, one of their valence electrons is located here. We're not really saying which p orbital. We don't know how many, right? Because we would have to list out kind of every possible quantum number that it has. So yeah, any one of those from boron to neon. Excellent. What about this one? Does it look good?
It's not possible.
So not possible. Why do you say that?
Because L is always equivalent to N minus 1.
Which one?
For the left row, from the top, second from the top row, from N is equals 3 to L equals 0.
The M sub L, you mean?
Yeah.
Yeah, so M sub L, we said has to go from negative L to positive L, but then you said, okay, well, this is 0. So what orbital is this again?
That's the s orbital.
So, right, some sort of s orbital. So yeah, there's only one option. So how can we correct this then, our M sub L?
L would equal 2, wouldn't it?
Yeah, if you wanted to do that, so that would be one way to change it. So we could do, 3, 2, 1, negative 1/2. I guess I was thinking, right, we could change this to a 0, and then that's something on the third row, S shell. So either way, right, so this would be an okay modification. This could be an okay modification.
If N is 3, does L have to be 2, or can it be?
It can be anything, so 0, 1, 2, 3. So it's just saying what's allowed, right? So going back, I think this is a good chart, right? Because we're saying, okay, N is 3, right? But then our options for L could be 2, 1, or 0. So yeah, those are all valid, right? Because we could say, oh, we have a 3S if it's 0, it's 3P if it's 1, or 3D if it's 2.
Does L have to stay smaller than N?
So yeah, L is always smaller than N, right? So going back to mathematically what's allowed, L is always N minus 1. But
It's possible for anything for any integer, as long as it's above 0. And
yeah,
less than
and
1
including
less.
0, yeah.
Including 0 and 1 less than L.
Yeah.
Okay.
So 2, 0.
Is it possible for them to have the same value?
To what have the same value?
L and N?
For L, M, and
For L to equal N, because L is always less than N, right? But
Yeah.
L to be equal, or no?
so they won't be equal though, right? So L is always less than N.
So it's at least 1 less.
Yeah. All right, so this one looks good. What about the third one? How does this look? Allowed, unallowed?
That looks fine to me.
So 1 vote for fine. Any other thumbs up done? So more thumbs up, so yeah. And then, so what element is this referring to? So what's the 2 again? The, which one? Yeah, it's the orbital, so which orbital?
Doesn't it? That would tell you the key. Or, wait, let me look.
Yeah, double check the numbers.
So if L is equal to 2, then it can be anywhere with, M of L can be anywhere between -2 and 2. So that would be a d orbital in the third shell.
So d orbital, so some sort of 3d. And again, we don't know which shell, right? We can't tell that much information. But then, okay, right, that means it's something with a valence electron in here, right, 3d. What about this fourth one here? So here's some no's. Why? Why not? What's
N
wrong?
can't equal L, it has to be less than L.
So n can't equal L. And so when I'm looking at this, right, I'm thinking, okay, our first energy level, we can only have s orbitals, and that's a p, so we could change that to 0. You could, of course, also have modified it. If we change, right, n to 2, we could do 2, 1, 0, 1/2. So that would be another valid way to change it. And then what about this last one?
No,
I see some no's, some yes. What's wrong with it?
the spin's always negative or positive 1/2, it's not 0.
So the spins, so yeah, good catch there on the spins. So we could just fix it to positive negative 1/2. Excellent. Other questions on this one? Feel okay?
What defines the range of M sub L?
So M sub L goes from negative L to positive L
Okay.
with integers including 0. Yeah, Chris.
If n is 1, is L always 0?
Yeah, yeah, because, and then, right, think, so the thing you want to be thinking of, too, is, right, repairing that statement with the periodic table. And then, right, you look at the periodic table, oh, right, that has to be true, because 1 refers to only this row right here, and then, right, there's only the S there before you move on to the 2. So that's kind of retelling you that same information.
So does M correspond to the row on the periodic table?
Yeah, at least right with the main marking. So kind of going in how I taught y'all to do the electron configuration, right? So this is the 1s, the 2s, 2p, right, 3s. So just like that corresponding. And yeah, those energy levels do match with the principal, right? So this is the 3s, this is the principal third energy level, 3d.
Means the N always equates to the row, or is there exceptions?
Well, it depends how you fill it in, right? So these do fill in for, right, these are the energy levels, the N, but that only works for right here, right? Because this is 3s, 4s, 5s, 6s, but then that's where you have to go back to the notes, right? Because this is 3d, 4d, 5d, 6d, etc. So, right, it doesn't just go straight across.
So does each letter correspond to a block on the periodic table?
What letter?
NLM sub L.
Oh, the,
One of them spin, but
yeah, so remember the L's correspond to the blocks, right? So I don't know if that would be useful. I don't have a periodic table. Let me grab one from somewhere. Oops. Sorry, I'm just trying to find a blank periodic table here. So yeah, if that helps you, right, you can block this out. Okay, this is my S block, which is, right, L equals 0. So it's just kind of re-emphasizing kind of the same information.
L can only go up to 3 then, if it corresponds to.
Well, L, so theoretically, right, it just goes by the mathematical equation. Right, so it just follows this mathematical equation of the allowed value is n minus 1. But then, right, kind of what exists, what we can see is, yes, we're just going to have 0, 1, 2, or 3, right, for the F. But then this is where we get onto, oh, okay, mathematically, we could predict other elements that are bigger, right? And these orbitals continue mathematically in theory, but yeah. So it's still allowed, but we're just kind of focusing on what exists, if that makes sense. All right, now I lost where I shoved my periodic table. And so, right, okay, P block, L equals 1. And then right, D block, so anything L equals 2. And of course, F block. Anything L equals 3. So that might help you kind of visually, because, right, again, it's a coordinate system in a lot of ways and telling us where our valence electron is located. And then the M sub-L's, of course, just track, but they end up being, right, the number of suborbitals in each subshell.
Those unit orbitals underneath the outer shell?
Yeah, like, well, talking about the, so M sub L, right, is then the individual, like 3p orbitals or individual d orbitals. All right, let's go back. So let's do, this is probably good quiz practice. So see if you can write, write your electron configuration for nitrogen, magnesium, sulfur, and neon. And then also write out the arrow notation. So using both of those.
For neon, do we have to still use the arrow notation, or we could just put it in brackets because it's a noble gas?
Arrow notation is just a little like arrows, right? So you still want to do that.
But can we use the shorthand method and just bracket it instead? Or would you rather have us go to the previous neon gas, noble gas?
Yeah, because I mean, you can't just have that be the answer for neon is be neon. what do we get for nitrogen? Does someone give me the electron configuration? Yeah, Camel?
So I did brackets, helium, and then, 2p, and then the 3, like, photo lines, and then put 1 air rotation.
Oh, so
Oh, wait,
drawing,
electron? Oh, yeah.
yeah, so I was asking, so first start off with electron configuration.
So then, yeah, it'd be the 2p, right? Or
Well, don't forget 2s, 2,
yeah,
and then,
2p, 3.
yeah. And then you were telling me, so you drew out some lines, so you drew out 3 p lines, right? And then how many electrons in each one?
1, that's 2 each.
So, excellent. And then, right, if you wanted to include the 1s, you know, you can. So generally, right, these arrow notations kind of focus on the valence electrons, but, right, it's not wrong, and, you know, don't forget about it. Yeah.
So with, writing it as 1s2, 2s2, and 2p3 still look good?
Yeah, so you just wrote 1s2, 2s2, 2p3, right? Yeah, so writing it out is the same, right? Because 1s2 is just helium. So either way.
Would that be arrow notation on the right?
Yeah, so this is arrow notation, and you could have written it in like boxes. So I don't care too much, right, if you write it out as like those 3 boxes and put arrows in there, you know, to as kind of like how your book sometimes shows it. So you could draw it like that. But this is just kind of my personal preference because, again, right, this is showing energy on this axis with more negative, right, going on the bottom, kind of going back to those conventions. All right, so what do we get for magnesium then? So what's its electron configuration?
This would be neon brackets, and then I think 3s.
3s, 2. So everybody like that? And so again, right, just practice writing it out or make sure you understand. So of course, this is just, right, our valence electrons. So we could have just drawn this out, right? We could think about those core electrons in there. So obviously, these are all going to be filled. So I'll just put core electrons. Again, just kind of showing that you know how to draw that. And then what do we get for sulfur? Yeah, what'd you get, Ben?
Neon brackets, and then 3s2, and 3p4.
3p4. So that looks good. So then we write out our 3p, 3s. I'll just focus on the valence for this one. So 1, 2, and 1, 2, 3, 4. And so then we can think about other questions that may come up on an exam or something. So we would also want to ask how many unpaired electrons. So this is interesting. So right from this, we can get more detailed information. So now we can say, okay, well, we actually have 2 unpaired electrons. So we could say that about sulfur. Yeah.
So the arrows represent the spin states of the electrons, right? When you're filling them in, do they always point towards one direction or spin, or is it pointing? Because I notice when you draw them individually on these unpaired, they're usually pointing up. But is that always the case, or is it like a 50% chance of them pointing down?
Yeah, I mean, it could probably point down, but yeah, I mean, I just always show it one way by convention, so yeah. and then neon. So let's finish up that one. What do we get for electron configuration? Oh, what'd you start with? Sorry. Oh, helium, and then what'd you say?
2s2.
Yeah, 2p6, excellent. And so now we can see, okay, filled orbitals. Right, we can say no unpaired electrons. Okay. Let's look at some other ones. Let's see. Let's look at this problem down here. So now let's look at, well, how many electrons would we predict are unpaired in the ground state for these atoms? And let's look at vanadium. So start with electron configuration, right? Write out those orbitals. What do you think?
Is the ground state just when the charge is neutral?
Yeah, when it's neutral and then it's not excited.
I think germanium would have 2 unpaired.
Oh, but we're looking at vanadium.
Oh,
So let's start off with, Ben, you want to give us the electron configuration for vanadium at least?
Yeah, so I did argon, and then 4s2 and 3d2.
So that looks good. So did everybody start off with this at least? And so right then the next trick is, okay, well we have to draw out our little orbitals again and actually see how we predict they would fill in. So 4s, and again just focusing on our valence. So we'll put 2 in our 4s, and then 1, 2, 3. So then how many unpaired electrons does that leave us? So 3, excellent. And so 3 unpaired electrons. And then, of course, this is where you'd have to do, again, some sort of studies to kind of confirm this and yada, yada, yada. So that goes into kind of other areas of research, but that's how you kind of confirm that. Let's look at, I just want to skip around for a second. And so this last part was pretty similar to your lab. And so first, right, we have to identify, is it excited or ground? And then, and it's saying, okay, these are neutral atoms, right? So they're not charged, but they're just excited. And excited just means they won't fill in order. And then, so let's try that. So let's look at the first one at least. Maybe try to look at all of them. I know we're running out of time. But at least start with the first one. Right, see if you can identify, is it excited? And then what's the identity? So what do we think for the first one? So first of all, is it excited? So yeah, so what do we think it's excited? Excellent. So right, we have to recognize that, okay, we didn't fill up that p orbital, so that valence electron got excited. So excellent, right? This is some sort of excited state. And so then, right, I would suggest you just tally up the total number of electrons, right? They told you it was neutral, so that should also give you the atomic number of protons. So what element do you think this is? So neon, yeah, and that's, I would agree with that, right? So 2 + 2 + 6, so that gives us 10, so that should be neon. Let's see if we can take a look at this next one. So again, is it excited? So yes, y'all are fast with that one. And then can we tell which one it is? Sodium. Excellent. All right, did you get a chance to look at this one? So excited, unexcited? Excited. And then which element? Helium. And then what about this last one? I heard two different answers. Right, so kind of, to me it looks like it's normal. So 1s2, 2s2, 2p6, right, just kind of double checking that it's filling. 3s2, 3p6, yes. 4s1, so where does that bring us to? What element?
Potassium.
Excellent, so ground, potassium. All right, well, y'all at least probably know electron configurations, it sounds like, so that's good. And so we're running out of time, so that's probably where we'll have to end. Tuesday, at least my plan, or part of my plan, is to go back and kind of do the math behind this. So we didn't really talk about it, but you had the Rydberg formula from your lab. So we'll just probably go over some sample calculations with that on Tuesday. And then, so like I said, we'll review. I'll see what materials I have for study. And so I have your quiz, so I'll hand that out. And the only reason why it looks so long is because I needed an extra spot. So question 10 asks the muddiest point. So basically, like, what are you struggling with in this class so far, right? What should I kind of hit for review on Tuesday? So that's the point of that question. All right, so I will hand this out. Again, you can, right, take your break if you need to take a break. Otherwise, you know, you can take your quiz. And then again, ask questions if you're struggling. Recitation is your chance to catch up.